Welcome back to part 2 of our discussion of the loads that are used as inputs to GLHEPRO. And as a reminder, we talked about this in the Introduction to Ground Heat Exchanger Design with GLHEPRO lecture, but if you took, for example, these are heating loads for a year for a building. It includes some hot water loads, which is why it's in a cold climate, which is why you see heating loads year-round. The blue here, these are the hourly loads for the year, and more or less these breaks are weekends when there's some kind of thermostat set back and not much hot water being used. And this orange line that runs through it, this is what we call our hybrid time step. So it's a monthly load here, January, February, March. And then at the end of the month, we have this peak that we superimpose on it. And if we look just at the month of February, you see that what we've done is we've represented the peak load for the month, which may actually be, say, over here. We represent it with a single rectangular pulse, right? And that's what we call hybrid time step approach. So again, this means that we have monthly heating and cooling loads, monthly peak heating and cooling loads. The question, if we go back a slide, is, okay, this peak load, it may well match this duration here. I think it does actually, 68.265, 68.265. It matches this duration, or this load, right? But it's not the same shape. How do we know how long this duration should be? And the way we do this is we use what's called a peak load. We call it a peak load analysis tool. And I think I mentioned in the last part that this is a spreadsheet. It was originally intended to be incorporated in GLHEPRO, but that hasn't yet happened. The theory of this is discussed in this paper by Cullin and Spitler. And what it does is it allows the user to determine the duration that will give the matching temperature response to the actual hourly loads. So again, going back, on this day we have this funny shape with this loads increasing at night, and then all of a sudden they shoot up when we have, I think it's a thermostat coming back from setback, right? And has this. How do we get this duration that gives the same temperature response? And that's what we're going to look at with the peak load analysis tool. All right, and as I said before, it allows the sizing to be done with relatively quick simulations and sizing in seconds, not in hours. Okay, so traditionally, or the most common application, right, is a ground source heat pump system with heating and cooling being provided by ground source heat pumps. Now, we may also have systems with other devices adding heat or extracting heat from the loop, but say typically we have a ground source heat pump system may have multiple ground source heat pumps. The building simulation tool calculates the loads for each hour on each heat pump, and we get those loads out and we add those together, right? And we add all the heat pumps, the loads for all the heat pumps that will be served by the ground heat exchanger. Right, so these are sometimes called block loads for the building. It's definitely true they are block loads. In fact, we don't have to calculate loads on heat pumps serving all the loads, serving all the zones. We could calculate a theoretical heating and cooling each hour for the entire building at once. That would also be a block load. But the outcome's the same. We're looking at what the net load is on the entire space at once. All right, and GLHEPRO, at least 5.0, doesn't have a way to input loads on different heat pumps individually. I considered that some years ago, may yet change it in the future, but at the time it seemed like it would be overly complicated to say, at least for an American system where you might have 15 heat pumps in a small office building or 30 heat pumps. I was trying to imagine users putting in each one of these sets of loads and specifying the heat pump for each one individually, and it turned me from trying to incorporate that. All right, so that's why we take all the loads together, and they're all the ones at least that are going to be served by the same ground heat exchanger. Okay, GLHE Pro has a feature where it will take two types of loads. It will take, there's two icons on the main screen of GLHE Pro, and I could even, here's GLHE Pro. Here's the two icons here and here. So we have GLHE loads, or direct loads on the ground loop heat exchanger, or heat pump loads. All right, and the direct loads are used for loads that don't come through a heat pump. So one example would be if you're building an apartment building in a place like Stockholm, Sweden, where typically they, first of all, don't use reversible heat pumps. They use heat pumps that are only provide heating. Sometimes they provide cooling by using ventilation air, and then what they might do is put in a heat exchanger that you circulate the fluid from the ground loop through that, right, in some type of fan coil unit, and it gives you what's sometimes called free cooling. It's not really free because you have to pay to use the fan, but you have to pay for the pressure drop across the coil, but you're not running the compressor, right? So if you do that in the summer, those kind of loads, which become they're cooling loads still on the loop, they're a type of direct load because they don't go through a heat pump. Likewise, you could do a very similar thing by preheating the ventilation air using the fluid from the ground loop. So, especially in a very cold climate, the temperature there coming back from the ground, it might be around freezing, but that still might be a lot warmer than the outside air. So you could possibly use it to preheat the air. You can also use this for a cooling tower or some other device where you reject excess heat. Now we have another way of sizing cooling towers. So this is it's not necessary to do this, but if you wanted to do it, you could model the cooling tower by figuring out how much heat it's going to reject each hour and put it in as a direct load. All right, the heat pump loads, in this case, and maybe I should say for the direct loads, if you specify a cooling load of 10 kilowatt hours for, say, a fan coil unit that's doing free cooling, it's going to reject 10 kilowatt hours to the ground. There's no difference between the two because we don't have a compressor. For the heat loads on the heat pumps, right, we calculate the heat rejection based on both the load and the heat pump entering fluid temperature, and maybe I should say a performance map of the ground source heat pump. So then the actual amount of energy the compressor uses has to be rejected to the ground. That depends on the heat pump entering fluid temperature. And so we use that information to figure out how much heat is rejected. Likewise, in heat extraction mode, it's based on the heating load and the heat pump entering fluid temperature. Right? And that is, we include the compressor heat. It's either subtracted from the heating load or it added to the cooling load to get the heat extraction for the heating when it's in heating, or heat rejection when it's in cooling. Okay, the loads are in GLHE Pro. They're treated. There's two different sort of places you input them depending on which of those icons you press. All of the monthly loads, heating on the heat pump, cooling on the heat pump, heating on the ground, cooling on the ground, they're all converted to a single monthly heat extraction rejection rate. And the peak loads, then, they're assumed to occur at the same time. So in fact, if you change the duration in the heat pump load, and you also have direct loads, it will change the duration in the other. So there's some limitations to doing both. But they're assumed to occur at the same time. And I should say, I should really correct this. This isn't quite right. Okay, I've corrected the slide here. The peak heating loads, both on the heat pump and the direct, they're assumed to occur simultaneously, and they have to have the same duration. The peak cooling loads, heat pump and direct, those are assumed to occur simultaneously, and they must have the same duration. But the two peaks are actually treated independently, and in the way it works in GLHEPRO 5.0 is that we compute the end of the month average temperature, right? And then we figure out, well, if we apply this heating pulse, what will we get? And if we apply this cooling pulse, what would we get? We don't actually have them interacting at the same time. They're assumed to occur, well, in one sense they're assumed to occur in the same time, in another sense they're assumed to occur independently. So it's a little bit of a simplification that goes with putting all these peaks at the end of the month. We'll discuss that a little bit more later. Okay, so you might say, well, this seems kind of complicated. Why do we need to compute this peak duration? Why do I need to use this tool? Right? And the answer is that buildings vary in the degree to which the design is dominated by monthly loads or by peak loads. So the monthly loads, they're more important if the annual load is imbalanced. The more imbalanced, the more important the monthly loads are, and typically the less important the peak loads are. Or if the building has short, sharp peak loads, those tend to be more important than, say, loads spread out and look like a sine wave over the day. Right? But it's difficult to predict in advance, and that's why we have a tool to do it. You may have seen some other methods that just suggest a certain peak duration. I think that limits the accuracy of those methods. So if you look at, there's another reference, Thomas Ray Young's master's thesis. It's listed in the reference section. It's available on our research group website. He uses an example of a small office building and what I call an idealized church building. And by idealized, I mean it's not used at all during the week except for on Sunday mornings for, say, 1 hour where 500 people or some large number of people come in and go out. Or maybe they're there for 2 hours. But the point is, it's a sort of an extreme example where the peaks are due to a large influx of people. Right? And of course, those two buildings are going to have different duration peak loads. And speaking of peak loads and dominance due to peak loads, and we're talking about how the sizing can be dominated by the peak loads, you can do this artificially. So in your simulation, if you have, say, a lot of heat pumps and you run the system with night and weekend setback, and they all are scheduled to come back on at the same time, you can artificially create a high peak load. And in fact, if we go back to the figure I was showing you near the beginning of this part here, I think that's actually what's happening. I think we have a night weekend setback and it shuts, it comes on. Now, maybe this isn't too artificial because the load doesn't fall off that much over the day. But you said this can happen in a simulation. It can also happen in real life, right? And in real life, it's fixable, though, by distributing the start time, and it's fixable in your simulation by distributing the start time. But you might just something to keep an eye out for. Some people run simulations that show an exceptionally high peak load, and you realize you had the building off all weekend. In fact, maybe it was Labor Day weekend, and you let the temperature in the space rise to 86 degrees or 30 degrees Celsius. And then at 5 a.m. on Tuesday morning, after a 3-day weekend, you turn on the system, and of course there's a very large cooling load to pull down the temperature, right? And yes, you can do this. It's not that the simulation's wrong. It's just that you've kind of used a simplistic input, and in real life, if you had this problem and realized that you might sort of distribute the start times a little bit. So start some at 4, some at 4:30, some at 5, some at 5:30, that type of thing, and you would get a better or less of a peak load. Okay, in terms of the theory, I'm just going to briefly mention there's a paper by Cullin and Spitler where this is all spelled out. One of the things that we did was we sized with an hourly simulation and with a hybrid time step simulation, and we looked at 48 different buildings. Right? And if you look at the difference between, if you say, well, the hourly sizing is correct, right? And of course it has errors related to material properties and other things, but it's I'll just say it's fairly accurate. Right, this hybrid time step approach can also give some errors compared to that. And if you look at it by oversizing, it's somewhere between plus, say, 8% and minus 6%. And if you look at other errors in the sizing procedure, like errors in the thermal response test used to estimate the ground conductivity, several of those other errors are on the order of plus minus 10%. So this is it's not an excessive error, but it is a, it does cause some uncertainty. And the causes in this, they're basically, you could say that using a single peak heating duration for the same length for every month, and this, or in the same length peak cooling duration for every month, can be one problem. The peak cooling load might occur in July, but maybe in August there's a peak cooling load that's almost as high, but maybe its duration should be different, and if that's accounted for, it would give a slightly different load or a slightly different size. Now, we assume the peaks occur at the end of the month, and they may not. They may occur earlier. All right, sometimes the day before the peak day has a little bit of an effect. So we're actually working on some research now, another tool that takes into account all these factors, and actually automates this. So that may work its way back into GLHEPRO. But right now in GLHEPRO version 5, this is one of the limitations. Okay, stop there.